So as I mentioned in the previous screencast, we get a plethora of structural information from a proton NMR. And so the first thing is the number of signals tells us the number of different types of hydrogen in a molecule. Then the position of signals will tell us what types of hydrogen the molecule contains. And then the intensity of the signal indicates the relative amount or how many of each kind of hydrogen there are in the molecule. And then the spin-spin splitting of the signal will give us further information of the neighboring environment for various hydrogens in the molecule. Right? So we're going to start in this screencast to just talk about the number of signals. We're going to look at the position and intensity and spin-spin splitting in some future screencasts. So right now, focusing in on the number of signals. So when we talk about the number of signals, the number of NMR signals equals the number of different types of proton in a compound. Right? And so the big thing here is that protons that are in different environments give different signals. Right? The other thing that's important is that equivalent protons give the same signal, right? So one of the ways to do this a lot of times is to look for symmetry. So for example, there's symmetry in this molecule. These protons are the same distance away from the oxygen as these protons, so they are equivalent and only have one NMR signal. This proton is in a different chemical environment than this one. They're a different distance away from that chlorine, so they're going to give two signals. When you come over here, right, you have the CH3 here, and that's going to give a different signal than the CH2. They're the same different distance away from the oxygen, but they're in different chemical environments because this CH2 is attached to this CH3 here. Okay, so they're in different environments there. Here's some other examples which I think are really helpful. Right? We see there's a line of symmetry here, so both of these are just going to give one signal. But if we look here, right, the Br and the Cl are different. And so where these protons are compared to the groups that are around them are different, and so they give three different signals. This would have two signals, this would have three signals. Now, there are a lot of ways to solve a problem, and so if the idea of looking for symmetry is not helpful, my suggestion is to replace the hydrogens with a more electronegative atom to determine if they are equivalent. So what do I mean by that? Well, let's do this example. How many kinds of hydrogen atoms does pentane have? Well, when we look at it, CH3, CH2, right? CH2, CH2, CH3. This is pentane. And I am going to number this 1, 2, 3, 4, 5, just to help us as we talk about this. So let's say we were trying to figure out if 1 and 5 would give the same signal. Are they equivalent? Right? And so I'm going to substitute in a chlorine. Actually, I'm going to substitute in a bromine, I think, because then we won't have to worry about C1 and chlorine looking alike. So we're going to substitute a bromine. So what I would do is I would say, okay, hey, look, if I were to take this molecule and substitute a bromine for one of the hydrogens at C1, would that molecule be the same as if I were to take and substitute a bromine at C5? And of course, you can name these, and if the name is the same, then yes, right? Those would be equivalent there. So what we can say then is that C1 and C5 would give the same signal, okay? Then, so this one and that one are equivalent. So then I would ask, like, well, maybe are 2 and 3 equivalent? Well, let's substitute in a bromine and find out. So we come here and we say, okay, CH3, CH, Br, CH2, CH2, CH3, and then CH3, CH2, CH, Br, CH2, CH3. And so we would name those two different things, right? This would be 2-bromopentane. This would be 3-bromopentane. So those are not equivalent, right? Alternatively, again, you can look for symmetry. We see there's symmetry right here. And so this would give us 3 signals where this would be A and A, this would be B and B, and this would be C, and that would be the third signal. So those would be the signals that we would see. We were going to do many more examples of this in class. So if you're a little uncertain, I'm happy to help. Let's talk about the number of proton signal NMR signals in alkenes. If you're comparing 2 hydrogen atoms on a ring or a double bond, the 2 protons are equivalent only if they are cis or trans to the same group, okay? So 2 protons are equivalent on a ring or double bond only if they are cis or trans to the same group. Okay, so let's look at an example of this. If we have a molecule that looks like this, and we have these two molecules, and they are on, this hydrogen's on the same side as Cl, this hydrogen's on the same side of Cl, then as the Cl there, then they are equivalent. But look over here. This hydrogen is on the same side as Cl, and this hydrogen is on the same side of Br, and so they are not equivalent. They will give you two peaks because they are in two different environments. Then if you look here, what we find is we'll get three, because this is on the same side as Cl, this is on the same side as hydrogen, so that's a different environment, and then this hydrogen is here next to Cl, so that's a different environment. So you have to be really careful with your double bonds. And let's look at rings too, right? To determine equivalent protons in cycloalkanes, you need to draw all the bonds to hydrogen and determine whether they're cis or trans, okay? So you need to draw this like this, not like this, okay? And so when you draw this like this, we can see like here. So this is drawn here. This is just cyclopropane. Cyclopropane, all of these are equivalent. But look, this is drawn here, and we can see that this proton is in a different environment and closer to the chlorine. And because this chlorine is up and these two are down and they're the same distance, they're going to give a peak, and then this is also going to give a different peak here because it's in a different distance from the chlorine. So my suggestion is to draw with the dashes and wedges, and then draw this as cis-trans, not like this. It makes it really hard to see. And so even though it takes up a little bit more space, make sure that you're doing that. Now, if you substitute these two atoms with some sort of more electronegative atom, I chose bromine in the previous one, and it forms the same product, then those are called homeotopic protons. So for example, there are two hydrogens here. These two hydrogens, when substituted in, are identical products. That's homeotopic. However, when you substitute these in, right, and that you can form enantiomers, then those are a lot of times, those are called enantiotopic protons, right? Okay. And then when you substitute two hydrogen atoms and they form with something more electronegative and they form diastereomers, those are called diastereotopic protons. So a few new descriptive words for protons in our NMR. So just these last few slides. If you have any questions, please feel free to stop by. Again, the big thing out of this screencast is identifying the number of protons, unique protons in a molecule.